Okay, hello everyone, and thank you for joining us for our webinar, How Utilities Can Use AI to Improve Water Asset Management. My name is Simon Cox, and I'll be facilitating the webinar today. It's a joint webinar between Oldcastle Infrastructure and our technology partner, VODA AI, and I'm delighted that we have two extremely good speakers for you. First up is going to be Jeffrey Johnson, who's Director of Water Innovation at Oldcastle Infrastructure. He's going to talk about some of the water asset management challenges that are facing municipalities and utilities today, and then explore how new AI tools present new ways of tackling those challenges. Next, we'll introduce CivilSense, an AI-driven water asset management platform, and explain how it's revolutionizing our approach to risk mitigation, leak detection, and failure prevention. After that, he'll hand over to Corey Sides, who's SVP of Sales at VODA AI, and Corey will take a deep dive into predictive leak detection. He'll give a demo of the CivilSense platform, and then he'll talk through some real-world examples of how the platform has helped utilities to understand the risk in their water networks and prioritize repair work to prevent costly, disruptive water main failures. We'll endeavor to leave time at the end for questions, so if you have anything you'd like to ask either Jeffrey or Corey, please submit your question and we'll address it at the end if time allows. If we run out of time, then we'll follow up with answers after the webinar via email. Okay, well, without further ado, I'll hand over to Jeffrey and we'll begin.
All right, thanks, Simon. Hello, everyone. Welcome to our webinar today. Really excited to see everyone here and to talk through not just some challenges that are facing water industry and utilities, but some solutions that we're really excited about, and we're really excited to partner with some wonderful technologies to bring these solutions to customers and to partners alike. So we'll get started just kind of setting the table for some of the challenges facing the water industry and utilities as a whole. And one big one that we should address is water scarcity. You hear all about folks working in the environment and trying to have a positive impact on it, and a lot of times you hear about temperature and carbon. But for us water folks, we know that water is kind of the sleeping giant of sustainability. And within that, water scarcity is playing a large role in the global water marketplace, as the numbers can be pretty staggering for water loss. When you look at, globally, almost 2.5 billion people live in water-stressed areas. And within that, 4 billion people experience water scarcity at least some point for at least a month of each year, which is pretty staggering. So then whenever you zoom in a bit more here, I know folks viewing the webinar will come from all over, but when you zoom in on the United States, where folks often take water for granted in different research studies, the reality is that the United States is not immune to this either. The EPA did a poll about 10 years ago, and they asked leads of water management districts across the country, were they concerned about water shortages, and 40 out of 50 states were represented with someone saying yes, that they didn't know where they were going to get their water in the next decade. And as I said, that survey came out 10 years ago, and here we are at the end of that decade, and the story is the same, which we'll see here on the next slide. But that's exacerbated by kind of the current state of our infrastructure. If you look at the different ASCE report cards that come out, we know our infrastructure is aging and failing in different areas. And globally, around 35% of all of our treated drinking water is lost before it even reaches one of our consumers or our customers. So that just kind of adds insult to injury on top of the water scarcity issues that we're facing. And so that in the U.S. alone, that number represents 6 billion gallons of treated drinking water that's lost every single day. So we're losing 2 trillion gallons a year in the face of water scarcity. And looking at this across the U.S., we have over 30% of our states are in the medium to high or extremely high risk for water stress. And we even have one of our states, New Mexico, that's in the extremely high risk. So you think of somewhere like in the Middle East, like the UAE, which is a desert country. Of course, we're gonna think of them as having water stress, but we even have one of our states here that's in uh, the same category as the UAE and California, obviously knocking on the door. Then when you look at other states that you might not even think of as being water stressed, like the Mid Atlantic or even the Southeast or Florida, for example, even they are included in this water stress for different reasons with populations and stressing their aquifers. So this isn't just a humanitarian issue; it's also an economic issue, and it's a problem for growth and development. So in Florida, we just saw that they're in the medium to high water stress zone. Florida is one of the two fastest growing states in the country, and it's growing so fast that their aquifers and water supplies can't keep up with the water demand. So, some of those areas are growing by over 30% in the next decade, and the water utilities, there might be some here on the call that they just are not sure how they're going to keep up with the growth that they're seeing, how they're going to be able to produce enough water to meet those demands. And then we're seeing that in Phoenix now, where Phoenix is not issuing permits and halting new construction approvals due to water supply shortages, and as they continue to fight over allocation of water with the Colorado River. So then with that, you have 12 states that require some water loss tracking and reporting, or maybe even some action on top of that, just to understand the baseline of what their water loss is, so they can do something to address that. Because as we look at um, finding alternative sources, kind of fixing your leaks is kind of the low hanging fruit when it comes to finding new water sources. Just try to save what you already have. But what we're seeing in some of these areas is extremely high loss rates, over 85% in some areas of Georgia, Chicago and Detroit, anywhere from 50 to 70% in their communities. And Jackson, Mississippi is a well-known example of issues with water utilities, and we're proud to have been able to partner with them recently on some work, but they've had loss rates of up to 65%. So again, just exacerbating these issues that are facing the water industry. So these challenges, are kind of bucketed across four categories. The way we see it's aging infrastructure, scarcity, which we've discussed, regulatory challenges. We talked about the 12 states that have rules around tracking water loss, and then resource limitations, right? We all know the kind of state of the economy, and budgets are tightening. But the growing demand for water, along with its unpredictable availability, and then you couple that with rising maintenance costs, treatment expenses, distribution challenges, that really underscores the importance of sustainable water management solutions, not just for today, but for future generations. And when you look at this, we look at kind of total asset management of our infrastructure. And when it comes to that, that's where tools like we're going to be talking about today are not just needed, they're essential. Because we know that managing a water distribution network is very expensive. The AS, American Society of Civil Engineers, ASCE, did a study a couple of years ago that found that maintenance, just to maintain the existing networks we have, will cost $50 billion more than the capital that we have available for those utilities. So we'll never be able to maintain them the way they should. Not to mention that we're still acting very reactively. About half of all of our maintenance work happens after a failure has already occurred, and this is largely not anyone's fault. It's been the nature of the beast, because um, an infrastructure asset has a set time span, and there's variance with that. But the typical piece of infrastructure, so your pipe or vault, is going to last 50 to 75 years. And most budgets reflect at max of a 1% replacement cycle. a lot or a 0.5% or 0.2%. But if you were at 1% replacement cycle, you're betting your money on your infrastructure lasting 100 years, and we know that that's the exception rather than the norm. So with that in mind, that's no reason that we're seeing issues with failing infrastructure driving a lot of this water loss. So with that, there comes in artificial intelligence, AI technology. So how does that help? How does that help our utilities and help solve water scarcity and help us better manage our water infrastructure assets? So where are most utilities today? A lot of surveys show, and I don't know if folks agree here, but that we're not really at a place where we don't have data anymore. We have data coming at us from every direction, right? Most people have GIS. There's some types of SCADA systems. You've got some work order management, maybe even sensors or even spreadsheets give you some data, but the limitation is that it doesn't really talk to each other, right? So the result is you're managing work orders, and that keeps you from being strategic. Your teams spend time putting out fires rather than trying to zoom out and look at the big picture. And if you are investing in sensors, you probably got more alarms than you can handle, and you're still getting caught off guard by pipe breaks and leaks. And you're trying to piece all this together into capital planning, and you're still kind of dealing with anecdotes rather than having defensible priorities. And we're moving a good direction, but that's no one's fault. It's the system or the lack of one that we've had to date. But that's the exciting thing about where AI comes in, is that it's about connecting the dots between all this. It's not about adding more noise. It's enabling action, making the invisible visible, helping automate decisions to reduce risk and increase efficiency, and streamlining operations, that these different data points you have in a spider web start to make sense and empower folks, decision makers, to build defensible capital plans and to make operations decisions that don't just make sense, but they deliver real return on investment. So kind of as I said, AI isn't just a standalone tool. It's an integrator. It sits in the middle and can connect the dots between stakeholders and functional groups. Here you see on the Venn diagram that kind of these key areas where it can really provide benefits are around risk management, and who here isn't concerned about mitigating risk and managing risk, not just on their budget planning, but even something like staying out of the news for the wrong reasons and being in the news for the right reasons. So you get transparency. You enable your auditing to be more accurate. You get to reduce your downtime, and it helps to start spotting trends to be able to have your costs be more predictable. And from getting on the news, it helps you predict where failures and breaks might occur, so you can do something about them proactively before a main break in a critical area ends up on the news. And it allows your operations teams to be more efficient. It allows real-time maintenance by looking at advanced modeling, increasing productivity, reducing truck rolls to go dig dry holes. And all of that kind of couples with your enhanced decision making of moving from reactive to proactive and automating some of your decisions where you can. It obviously doesn't replace people. People still have to be able to make sense of what it's telling you and to follow through on the actions, but it helps make jobs easier. And then the folks that can use it and benefit from this are not just utilities themselves, but it's the public. Can have improved transparency, obviously reduced cost, and avoiding disruption, but working your way up for your other customers, your industry. If you've got data centers, you've got manufacturing, those are big, important customers, and you can drive value for those customers and recruit and attract new economic opportunities in your area because you have a good control over the supply of water for some of these industries that really require efficient delivery of water. Operators, we've been talking about that, but even your regulators to be able to automate some of your compliance, not spend so much time in your compliance documents, and to be able to build budgets and defend them with data is big for trying to go get some of this available funding through state revolving funds or through IIJA money. So AI enables all of this. So then kind of what does this look like tangibly? The idea sounds great, right? I can wave my hands around and say how amazing it is, but let's kind of talk through what does this look like in action? So when we look at leaks on a network, and this is an area of great importance and interest to us for the reasons we've discussed, and then obviously Oldcastle, we manufacture more infrastructure than anyone else in North America, and then this is an area we're keenly interested in. We know, 35% loss rate. That's significant, unbelievable, really. But it is what it is. It's like, imagine Chevrolet manufacturing trucks and delivering them to the dealership, and one out of every three trucks falling off the transport vehicle on its way, and just that's them accepting that's just how business goes. But for us, we're excited that we're able to start making a dent in that, and we can take tools that have been around and improve them. So we look at acoustic sensing. It's been a reliable technology for leak detection, but how do we take that and make it better with AI? And we're excited through CivilSense, which is our our platform for infrastructure intelligence and smart infrastructure, that we can use machine learning AI tools that can pull in all this acoustic data from sensors across the network and be able to provide actionable insights around potential failures, leaks, leak sizing, and actionable insights if you do have a leak, to say this is how big it is and this is exactly where it is, so the customers, utilities can be informed to do something about it. And as the power of AI and computing grows, to be able to continue doing it better and better. With these things are machine learning, it learns from itself and continues getting better and better. And that's why we see our accuracy continuing to improve, and right now at a market leading 93% accuracy when it comes to actually pinpointing leaks using AI. And this has really been kind of exploding here the last 5 years. We've seen that across every aspect of our daily lives, right? Of our phones, and well, you can't go on Amazon or some website without some AI tool trying to help you or get you to buy more in some ways, or help your email sound better. But the same holds true across all of the AI, is that it continues to improve, and the value of it is taking intricate data and trying to make sense of it in a way that has consumed hours and hours and hours of human effort, and taking some of the guesswork out of it. So, the way it works for us is we have sensors that are highly engineered, that are integrated within our AI that can take a lot of the human error out of it, and we can get that accuracy so high, as I mentioned before. And you can do this in a completely non-invasive way. There's no permanent attachments; they're just temporary sensors that don't interfere with any of the infrastructure, and they're able to listen for discrepancies in what is expected. The sound of water is expected within a pipe, so it can listen to vibration or noise, and then the AI is able to. The AI we use has been trained on over 1 million different data points and growing every single day, so it's able to start to filter out background noise and external noise, and also based off of physics and the speed of sound through different materials, it can distinguish between different pipe materials and sizes. That's the amazing thing about the the AI is that, we'd like to know, pipe size and material to help optimize the placement of these sensors, but the AI itself is good enough where it can actually tell you what the pipe material and size is without you telling it itself. And all that's because of the machine learning. And it can distinguish between water flowing through various systems, joints and T's and elbows and reducers and all the valves, all the different things. As the more it hears, the better it gets. So the way this works for us is, um, we deploy the sensors across a network, working with the utility. Again, we kind of get the data on kind of pipe size and material, so we can know where to place the sensors, because as you can imagine, the distance sound carries is different based off of pipe size and materials. So we want to make sure we've got our sensors in the right places to get the best data, and then the AI takes it from there. It's able to assess risk and detect leaks. It can do the exact size of a leak, so you can prioritize. We always say you fix the worst first, and we pass that data along to a utility. We can even set some thresholds around, hey, we can band leaks by size, so we can make sure we're getting the right frequency of reporting to you with the right prioritization. And then we have field crews that work for you, that go out and not just deploy the sensors, but are able to validate that the leaks are occurring in the high priority areas, and we'll mark up on the ground with an X, with us saying that if you dig here, you will find the leak. That's how confident we are and how precise the system is. And then utility repairs the leaks, and our sensors are able to then validate that the repairs were successful. We've seen plenty of cases where repair has been made, but it's still leaking a little bit, and so maybe the contractor has to come back out and fix something. So we're able to provide that as well. And kind of a look at the comparison. This process we stand by because we have a 93% accuracy and getting better every day, whereas the kind of traditional acoustic leak detection is 30 to 40% accuracy, because it's so dependent upon human experience and the ear of the person listening, how long they've been doing it, and how well they can pick up kind of the fine differentiation between a large leak and a medium leak, or a large leak across different pipe materials. As we know, so many networks are kind of a patchwork of materials across, iron or plastic or asbestos cement or various types of materials. So the AI is able to take that human error out. So that I mentioned before, that allows utilities to start to shift from this reactive. I said that 50% of all of our maintenance events occur after a failure's occurred. We want to become more proactive. So how do we stop reacting to breaks and doing something before they occur? And that allows us to shift toward continuous monitoring and taking all the data that we've been receiving and making predictions off of it, using predictive analytics with broader data sets. And as I said before, make sense of all the data you have. And how do you take that information and inform your capital plans? So you have a certain limited amount of money and you want to maximize your return on investment. How do you use this to inform your CIP and your budgeting? And this is coming sooner than later. In fact, it's today. A great aspect of it, where Corey is going to walk us through here in just a few minutes, and then it's just going to keep getting better and better. And that's what we're really excited about. That this kind of all is a flywheel, right? Once you get started, it's going to keep spinning and get easier and easier. And the true success, it comes when it points toward an action, and a proactive action. So kind of taking the leak detection that we started with, how do we move that to a more proactive asset management program? And so that is incorporating, partnering with folks like VODA to bring predictive analytics into the fold. So rather than just finding leaks that are already occurring, how do we predict failures? Um, how do we pinpoint areas of concern within a network so that you can be more proactive? So how do we couple these two things together to make something that really drives value for utilities and for our customers? And so we really feel like that's around um, prediction, prioritization, and optimization. And mostly it has to be scalable, which you kind of see there on the last bullet points. It's got to be something that is unobtrusive, and it's got to be easy to deploy, and it's got to be quick to drive value for customers. So I know with time and with budgets, we just don't have time to wait forever to really realize the benefit. So we have to be able to do that right away. And we're excited that our solution can, and hopefully you'll see that play out here. So how it works is, and Corey will get more into this, we pull in the most robust data sets that we can, working with utilities that we're partnered with. So pulling in your GIS data, pulling in publicly available, climate data sets, soils, census data, your historical breaks and maintenance events that you performed on a network. And then we use all that to build the models that help us forecast future failure, your vulnerable points, where you're expected to, we expect you to have issues based off of consequence of failure and likelihood of failure. So that's how likely it is for a failure to happen, and then how bad is it going to hurt you? That was the consequence if it does happen. So, for example, if a line breaks out going to a 5-house neighborhood in a field, it's going to hurt, but not as bad as if the main supplying the area hospital breaks. So how bad is it going to hurt? And then how do you combine those two things into a business risk exposure to help you mitigate your risk and prioritize your planning for potential failures. And then we take that, say these are your areas that are most likely to fail. So let's go be strategic and deploy sensors in these areas so we can find the leaks that are occurring because they're most likely to be in these areas. And then we let the AI go to work and provide, again, a maximum ROI and pinpointing where exactly these issues are occurring for our customers. And then within that, we want to be able to be verifiable and build trust with our customers. So we want to be able to report real time in a cloud-based platform for the predictive and the capital planning tools, but then on the boots on the ground with our field teams and our engineers that are doing the next level down leak detection that's prioritized based off of the predictive analytics, constantly informing our utility partners on what's being found, working with utilities on what data they have for flow and sizing leaks so that we can validate these for your audits that you might have if you're in one of those 12 states or you're independently performing audits on your network to provide your non-revenue water reduction reports to help you validate how much you're saving. And then API data integration as well. You'll want to be able to provide real-time access kind of both ways for us to be able to get the data to maximize the solution that we're providing, and then for you to be able to get the data back that you need into your systems as well for enhanced insights. So with that, we're really excited about the technologies we have that are able to help utilities identify and size their leaks and act with some expediency and accuracy and optimization. And, we hope that this is able to prioritize and transform how we manage non-revenue water. So I'm excited now. I'll hand it over to my colleague, Corey Sides, who will walk us through how the predictive capabilities can complete the picture and unlock real-time decision-making power. Thanks,
Awesome.
everyone.
Thanks a lot, Jeffrey. Great stuff. Jeffrey, can you confirm you're seeing my screen now?
Yes, I can see it.
Awesome. Yeah, much appreciated. So what I'm going to do is I'd like to just first walk you guys through some results that we've been able to achieve through our predictive modeling engine, how we typically measure accuracy. I'm going to give you a really quick kind of 30,000 foot view of the software. We'll do a little live demo. And then I'm going to walk through a couple of real world utility case studies and highlight some of the business results they've seen through using our AI driven solutions. Now, I'd like to start by just kind of highlighting and showing the improvement in accuracy and performance that machine learning can provide over and above traditional methods of ranking pipes, such as the age or the break history of the pipe. Now, as Jeffrey talked about, one of the things we like to do is make the invisible visible. Utilities across the country have often had a hard time trying to determine which pipes are in good shape and should be left alone, and which pipes are in bad shape and should either be replaced or inspected or targeted for activities like leak detection. And the reason is there's very limited data for decision making. And so utilities have typically relied on a very small number of data points for calculating the likelihood of failure, with the two most prominent being the age of the pipe and that pipe's break history. And that's what we're showing here in these top two graphs. So we've ranked every single pipe segment at a particular utility according to its break history or prior failures. That's what's in the top left. And then that same utility with all pipe segments re-ranked by the age of the pipe in the top right. Now, each of those dots that you see next to the rankings represents a main break or a leak that occurred at this utility in the year following these rankings. And where did that particular pipe fall up and down within those rankings? Now, we've color-coded the breaks to show which ones were what we like to call first-timers, meaning that that particular main break or a leak was the very first time that that pipe segment had ever failed, at least within the work order history. And those are what you're seeing in blue. And then repeat offenders coded in red, those are breaks or leaks on pipes that had already failed in its history. It had failed, once or twice or multiple times in the past. And now you can see at this particular utility, break history or the prior failure ranking does a pretty good job of putting pipes that were going to fail at the very top, but those are the ones that are in red. Now, what that means is that most of their failures are failures that are occurring on pipes that have failed before and are continuing to fail. And so ranking by prior breaks does a good job at picking those. But it's obviously no help at all in predicting those blue dots that are kind of uniformly spread up and down the rankings. If you look over at age, it gets kind of an amorphous blob of both old and new failures pushed kind of near the top, but really age was not a very good indicator at this utility. However, if you look at the graph on the bottom, that's the results from our machine learning engine. We were able to accurately predict more than twice as many failures as just break history alone. In fact, we were able to predict half of all this utility's breaks and leaks that occurred in less than 1% of their system. And as you can see by all those blue dots at the very top, almost half of all the failures that we did predict were on pipes that had never failed before, which was very impressive to these guys. So what this kind of tells you is that machine learning is really good at identifying buried patterns within the data. For example, it looks at things like pipe material and what type of soil is the pipe installed in and its proximity to things like roads or buildings, traffic patterns. It looks at weather patterns and so forth. It looks at where pipes have failed in the past, and then it learns from all those patterns. It learns what factors were present or leading to those prior failures. And then it takes what it learns and uses that to predict which pipes are the most likely to fail next in the next 12 months, the next 5 years, 10 years, and so forth. And that's what we provide back to clients through our software. And now, really quickly, I'm going to do a 30,000 foot flyover just to kind of show you the highlights of what you can get through the software. So you guys should now be seeing some GIS data on an Esri map. And so I'm just going to walk through a couple of key features that I'd like to highlight. The first one being the likelihood of failure. And the likelihood of failure is purely the results from the machine learning engine over whatever time window you want to look at according to likelihood of failure. So I can highlight which pipes are the most likely to fail. I could look by particular segment, or I can look by length. I can take a look at it by feet, miles, whatever. In this case, I'm going to say, hey, just show me the 10% of my system, which is the most likely to have a break or a leak in the next 12 months. I'm going to hit apply. And then it's going to populate both this map as well as a table. Anything that you see within the software is exportable. So you can take all of these results, whether it's likelihood, consequence, risk. You can export this as spreadsheets, shape files, or geo packages. You can also do some pretty cool filters and querying, a lot of trying to make it easy to get the data. And you can do this, really on any of these modules. But for example, let's say, hey, you were focused on a particular material. Maybe you said, hey, look, I just want to look at my cast iron pipe, which is in the top 10% most likely to fail. And then it's going to give you those results here. With any of this, you can click on that particular pipe. It's going to navigate to you and give you some information about it. So this is the #1 most likely to fail pipe within the system. It's a 4-inch cast iron pipe installed in 1913. It's had 5 prior failures, and our AI is calculating it's got 0 years left of remaining useful life. You could spend a lot more time. You can create saved queries and views. I'm going to pivot over now to consequence of failure. And, Jeffrey highlighted it earlier, but consequence of failure really, it doesn't take into account the likelihood that that pipe might fail. It doesn't matter for consequence. It just looks at each and every pipe in your system and says, if this pipe were to break, how painful is it going to be for me? And we provide some really cool tools for you to customize and really make this applicable to your utility. Or you can actually just use our default settings. So by default, we have particular parameters that we bring in. Those are things like what type of road does the pipe run along? The pipe diameter. Is it nearby things like hospitals, schools, or health centers? You can bring in paving data or pave dates, things of that nature. You can also calculate it by impact, or we've had a lot of clients that wanted to monetize their consequence of failure, so we provide those tools as well. You can use the defaults, or you can really customize this. As I said, you can use our tool to create special regions or areas or pipe attributes, or you can bring in custom layers. So for example, you might say, hey, I've got layers for my historic district or for fresh water bodies. Bring those in and create consequence of failure attributes. Those get assigned and looked at across every pipe in the system, and you get a really good view for every single pipe of what the consequence of failure for that pipe is going to be. And then the last thing I wanted to highlight, Jeffrey mentioned on, sometimes it's BRE or business risk exposure. Really, this combines the likelihood that that pipe is going to fail with the consequence of failure, right? It puts those two things together, and that really helps you understand the financial risk of any asset, and you can run those queries and get that data. Now, one of the questions that a lot of our clients would ask us is, hey, I've got this shotgun blast across my system. I'm not going to go replace one segment here, one segment there. I'm not going to do leak detection or inspections or condition assessment in that manner. So what does this tell me to do, and how do I get, more use in decision making? And so to do that, we have a really cool module we call Planner. And what Planner does is it takes certain activities like I just mentioned, whether it's replacement, rehab, condition assessment, and it uses those risk results to help you get the most value out of those projects. So for example, I'm going to pop up pipeline replacement. I'll go in here and we've got particular settings. So for example, you might say, hey, we replace at a neighborhood level, or I don't want to do any replacement that's less than 500 feet or more than 10,000 feet. There's cost settings based on what it costs you to replace pipe or do condition assessment. You can choose how you want to prioritize. You also have business rules where you can select, hey, how do I select which pipes I want to do which types of activities on? So in this example, I've said, hey, I want to do pipeline replacement when the risk rank is in the top 20%. So it's a high risk pipe. And the remaining useful life is less than 20 years. So, it's getting close to the end of its useful life, ready to come out of the ground. You can build a lot of really cool logic trees to help you with that pipeline selection. I'm not going to make any changes. And then you can come in here and put in a budget. So for example, I've got $10 million to spend over the next 12 months. How do I take those risks, take that into actionable projects for pipeline replacement? So it takes your budget. You can also put in goals that said, hey, I want to lower my non-revenue water by X in the next 5 years, and it'll help you build budgets and projects to get to those utility goals. You can edit these. So for example, if I wanted to look at this one and say, hey, I happen to know that if I'm in this area, I'm going to add this pipe as well. And so you can really customize those. You can save them. You can put in project start dates. You could choose to replace a certain material and size. Maybe you're replacing 6-inch, cast iron with 12-inch PVC. You can put that all in there. You can save it. Once you've saved them, you can run a lot of cool reports like show me the impact on my remaining useful life. Show me my cost over time. You can do a lot of great stuff with that. So I just mentioned remaining useful life. One of the things I'll do is our analytics module. So we take the likelihood of failure results from DaVinci along with a lot of industry data and use that to calculate remaining useful life for your entire system to help you understand which pipe segments are hitting the end of their useful life when, so you can help better understand the capital investment needed. You can click on any of these and it'll take you to those pipes. We also have a lot of other cool stuff. You can look at that broken out by material. You can look at things like, your failure rate by condition or by material. You can look at the makeup of your system. And again, all of this data is easily exportable as spreadsheets, PDFs, or whatever your need is. So just wrapping up, everything that I've been showing you is really around water mains. We also have similar services, though, for wastewater mains and service lines and laterals. You can also upload data, maybe things like want to look at my hydrants or look at where have I had failures in the past. We've got a lot of other really cool tools. You can create heat maps to kind of highlight areas where you need to focus. So I could spend a lot more time on it, but just in the interest of time, I'm going to go back into our presentation and go through a couple of case studies. So what I really want to do is highlight a few customers and how they used our results to get, real tangible business results, and really two distinct areas I want to focus on. So this graph kind of highlights those two areas. So these are the results from a large utility in the Southeast US. They had over 5,000 miles of pipe, and their average failure rate expressed in terms of breaks or leaks per 100 miles is around 15. That puts them right at the dead center of the industry average for a large utility in the Southeast. However, if you look at the very top of our machine learning based rankings, those are the pipes all the way up here most likely to fail. And you fast forward 1 year, the actual failure rate in the top 1% of our rankings was 370 breaks or leaks per 100 miles of pipe. That's 23 times higher than their average. So the two kind of areas where we like to deliver value is up here at the top of the rankings. That's where we say you should prioritize activities, preventative maintenance, replacement, and rehab. But the second area is also down here at the bottom. And a lot of people don't talk about this, but there is huge value in knowing which pipes to leave alone. So for example, the bottom half of this graph represents close to 3,000 miles of pipe that had a total of 6 failures. You don't want to touch these. So as I said, now let's look at a couple real world use cases for this data in both those two areas. So the first client we wanted to talk through is a large utility in the Southeast US. They've got over 3,000 miles of pipe, roughly 200,000 services. They've trusted our AI models to help with their planning since about 2022, have had great results. Now, this particular utility had a very high leakage rate on their smaller diameter pipes. And so to address that, they invested in some satellite leak detection work, which highlighted over 600 areas of interest for them. And while this was great, it represented way more mileage than they had time to inspect using their in-house crews. And they were really struggling to try and go investigate all of them. And in many cases, they were struggling to find the leaks within those areas of interest. And so what they decided to do is say, hey, let's take those areas of interest, import it into VODA, and let's overlay the areas of interest with the predictions from the likelihood of failure results, where we highlighted pipes most likely to fail. And let's exclusively focus our efforts where both those systems either overlapped or intersected or right next to each other. And so the result, by taking that approach of overlaying the areas of interest with the pipes AI said were most likely to fail, was that they were able to find leaks significantly faster with much greater success. They actually calculated that they saved 71 million gallons of water just last year by using machine learning to better target their leak detection program. You know, that's enough water to service almost 650 homes, again, by knowing where to focus those efforts and resources to get the most value. That particular example on the right of your screen just highlights kind of one particular case where they were struggling to find the leak within that area of interest, but just adjacent to the area of interest that was highlighted was one of the pipes that our machine learning engine said is very bad shape, highly likely to fail. And that's actually where they ended up finding the leak. It was just outside of the area of interest, but because of the soil conditions and other factors, the water was settling in a different area. Again, highlighting by targeting those leak detection efforts, we're going to get the most value. The second case study that I wanted to talk through, this is another large utility. This one's actually in the southwestern United States. They have around 4,000 miles of pipe, about 250,000 services. And the challenge they had is they were facing a huge repaving initiative where the city was basically repaving most of the entire city over a several-year period. And obviously the utility couldn't afford to replace all of their pipes. And so they had to make some really tough decisions on which pipes were they going to leave alone and which ones were they going to replace. And so they turned to our AI-based likelihood of failure results, as well as our remaining useful life tools. And by focusing on those two areas, they were able to work more closely with their local DOT and actually work together to better plan and schedule the work with more accurate data. So they were able to actually align a lot of the paving work to align it with the remaining useful life, saying, hey, can we push these areas to the end of the project because we think these pipes have got another 5, 10, 15 years on them. In many cases, they were able to convince the DOT to adjust the type of work being done. That is, if the pipe had a long remaining useful life and a low likelihood of failure and they wanted to leave it in place, in many cases, they were able to negotiate to shift from a complete repave and instead just do a resurface so that they could leave those pipes in place. Through all of this effort and coordination, they calculated that they saved $5.4 million just last year and not replacing good pipes. And that's going to continue to grow as they continue to drive this program over the next several years. And again, this is how you can get value in knowing which pipes to leave alone. We work with utilities all across the country. And one of the things that we hear regularly is that, the budgets just aren't enough. And so they need to do a lot with a little. And so these two use cases are really just designed to kind of highlight how having better data and understanding the condition of your pipes can help you get the most out of your budget, whether it's a lot of money or a little money, you want to spend it in the best way possible. Would love to talk in some more detail, but at this point, I think I'm going to pass it over to Simon, who is going to take some questions from our team.
Thanks, Corey, and thanks, Jeffrey, as well for kicking us off. We have had some questions come in. I think, Corey, first one for you. You may have touched on this in the demo, but the question was, is the system applicable to wastewater collection systems? And maybe you want to expand on that briefly.
Yes, absolutely. So we do work with both water and wastewater. We work with both gravity and force mains. The platform is very similar. There's a little somewhat subtle differences in that when you look at a wastewater system, failures tend to manifest themselves in different ways. Like you might have an overflow, and that overflow could happen down here, and it could be associated with a cave-in or a structural failure. It could also be associated with, things like fats, oils, and greases or buildup. And so it's a very similar use case, very similar tool. Sometimes we'll dissect the actual failure modes into more granular failure types, just because it's different from water, where when you have a break or a leak, water just comes out. So hopefully that answered the question.
Thank you. And on a similar subject, we also had a question. I think this is very interesting. On the wastewater side, could this be used to identify the best places to treat odor? And if so, has this been done anywhere?
I think the short answer is that it could be. We have not tested it on that yet. I think that I can answer a lot of questions. When you look at machine learning, it works, and it works really, really well. You just have to answer kind of two questions. The first is, do you have enough unique training data? Meaning, do you have enough cases of, hey, odor was reported here or there or here, or again, I'll call that the training data to train the model on. And do we know what the correctly associated inputs that go along with that, right? So do we know what type of questions to ask for to put into the model? And as long as the answer to those two things is yes, you can really train a model on a lot of really cool stuff, failure modes, and things of that nature.
Thank you. Next question is, do you offer a cartograph, OpenGov asset management integration? And if so, have any customers done this yet?
We have beta tested that with a client in Texas. So I don't know that we've actually deployed it. We do have a client in Texas who is using Cartograph and wanted to export our risk ranks, LOF, COF, things of that nature, and take that into their platform. And so we've scoped it out and piloted it with those guys, but have not actually implemented it anywhere yet.
Thank you. Next one is, could you transfer this information into the capital planner to create upcoming plans for preventative maintenance and capital improvement projects?
Yeah, I'll take that one too. I think the answer to that is yes. There's a lot of really cool capital planning tools out there. We've worked with several, so I wouldn't go so far as to say we work with all of them. But our goal is to make this data easily accessible, whether it's through APIs or file transfers to whatever in-house tools that our clients are already using. And so we have done that, probably with some, probably not with all of them.
Thank you. Next question. We've got a fair few questions coming, so I hope you're okay fielding these. Next one is, does the model give reasoning on a per pipe section, such as the main reasons the model believes for the likelihood of failure?
Great question. And the answer is sort of. So one of the things that we provide is what we call feature importance. And what feature importance means, it says, of the data that goes into the model, and maybe that's soil type or weather patterns or pipe material or any of these other factors, what inputs are having the highest effect on the output? So we can provide that in terms of, hey, these are the inputs that are having the highest effect on the output. One thing that I always caution utilities and customers, though, is that we're measuring correlation and not causation, right? So, for example, I always say, hey, we might tell you that the age of the, or not the age of the pipe, we might say, hey, the year of install is having a high level of influence on the likelihood of failure. And some folks will say, hey, well, that means the oldest pipe. And I say, well, no, age is a different input than year of install. And then they say, well, hey, maybe it's material. And I say, well, no, material is also a different input. And they might say, well, hey, maybe it was a bad batch of pipe or something like that. And that's very possible. But I also say, hey, it's equally possible that you had one or two particular contractors who were doing the vast majority of the installation during those years, and they were not installing it correctly. So that would something where the model would highlight that as that, hey, the year is influencing it, but it's not necessarily going to tell you the exact cause. It's just going to tell you what correlates with failure. Hopefully that answers the question.
Thank you. Next question is the remaining useful life based on industry standards or based on the likelihood of failure that the model develops?
And the answer is both. So we take industry standard or industry published data from AWWA and other organizations that, will bucket pipe material and expected useful life by region and material and diameter and utility size across the country. So we have that library. And then we take our likelihood of failure calculations, which is the AI generated results saying which pipes are more or less likely to fail. And then what we provide to our clients through the user interface, the best way I can describe it is a blend of industry data blended with the result. The industry data is kind of I'll call it a bracketing or a sanity check to make sure that it's falling within, reasonable accepted ranges, blended with the likelihood of failure. So it's about 50-50.
Great. Thank you. And I think relating to that also, how does the accuracy of the model's capability vary with the level or amount of data available?
Again, great question. I think I would just say the most important piece of data usually is the break history. We have a lot of folks that say, hey, we don't think our GIS is good enough. That's a very common objection I get. And what I'll usually tell people is don't let that be a blocker to having a conversation. In my experience, most utilities GIS data is never as good as they think it is and never as bad as they think it is. We've never met a utility that had some form of electronic data that we weren't able to work with and generally get what I would call really good results. The biggest swing in accuracy is around having enough failure data to train a model. So the less failures you have, the less the model has to learn from and find those patterns. And so if there is one piece that's more critical, it's having a high amount of failures. We like to see a few hundred if we can. Some folks will ask, hey, how many years back do I need to go? And it's really more about the total number of failures versus the years of history. Having both is great, but ultimately, the biggest kind of change in accuracy is around that failure data, having enough of it. We've run models with really small customers that had very few breaks and gotten excellent results. I would just say that the deviation year over year is going to be greater, and your confidence level is going to be a little bit lower when you don't have as many failures to train on. Hopefully that's helpful.
And is there anything you can do or the organization could do to help customers to build that data or improve the data quality?
Yes, is the short answer. So a part of our onboarding program is organizing the data with our clients in a way that is organized and helpful for ingestion into the model. That's just a standard part of our program. A lot of that is automated. We have tools that we've built to make that go quickly and take that lift off of our clients. I'll just give one example of the common things we spend a lot of time on sometimes is when we get, for example, failure data from a utility, it's not always associated with an asset. We would love it. And I always say, just as a public service announcement, best practice is to associate failures with assets. If you're not doing that, and tomorrow's a great time to start. It's fairly regular though that we'll get failure data that simply has the nearest address. Like it'll say, hey, we had a main break at 123 Main Street. And in that situation, our team, we do a lot of the work. We have to go through and geocode the failures. We've learned kind of some things that'll help us get it as close as they can to the nearest pipe. We run logical checks to make sure that if the work order data said it was a failure at this address on a 6-inch, ductile iron pipe, is there a 6-inch ductile iron pipe at that address, right? And so we do a lot of that work within our team. Usually that's the biggest improvement that we make or that needs to be made is associating failures with assets. And again, a lot of folks are already doing that. If you're not, I recommend that as best practice.
Thank you, Corey. Great answers. Would you mind flipping onto the final slide for me there? Yeah, we're up on time, and I want to be respectful of everyone's time. We do have some more questions that came in, so what I propose is we'll take those offline. We'll craft some answers and get them back to you via email. But as I say, we need to conclude the webinar here. So I'll finish by saying, Jeffrey, Corey, thank you both for providing an excellent presentation, and to everyone who attended, thank you for joining us. If any of you do think of any other questions, you can see Jeffrey's and Corey's contact details on the screen now, and I'm sure they'd be happy to give you further information offline. We did record the webinar. We'll make that recording available for you soon. Just in finishing, I'd like to thank you again, say that I hope you found it valuable, and then I hope you'll be able to join us on one of our webinars very soon. I hope you'll take care.
Thanks, everyone. Take care.